And this is?
Mr. DeRose.
And we're going to be talking about fire today.
As you just saw, the pretty colors in fireworks have been amazing us for years. Have you ever looked up at the fireworks and said, oh, that's blue, and I really, that's my favorite one. Oh no, the red one, that one's my favorite one. But I bet you've never looked up at the fireworks and said, oh, red, strontium, my favorite. Well, strontium, I'm not making up words. Strontium is an element from the periodic table. It's a metal. Strontium burns a very vibrant, bright red. So how does that happen in the fireworks? Well, if I were to make some fireworks in my backyard, which you can't do, number one, you don't have the equipment. Number two, you're not licensed by the state. New Jersey is extremely strict. Please don't try this at home. But we're in a chem lab, and I can try this on a very small scale. So here in front of me, I have four very popular colors for as far as fireworks go. I have some copper. I have the strontium, of which I just discussed, potassium, and some sodium. And I'm going to burn them all in a certain way. But before I do that, set up here as a demonstration, I have very small fireworks. The fireworks that are actually legal in New Jersey are sparklers. I'm going to light each one of these sparklers, and what you're looking for, the audience, is a color in the sparklers.
Should I back up?
There's a green sparkler. A red sparkler. And lastly, that's having a hard time taking off, is a white sparkler. Now I happen to have these at home. We like to play with these on the 4th of July. Each of these sparklers burned a different color. We had yellow. This one was supposed to be yellow. Red, green, and this one's trying its best as white. These sparklers have elements laid in them with the flammable material, which allows them to, as they burn, get the electrons in those metals really excited, and then they start to glow. Now I said words like electrons and the metals. This is a chemistry lesson after all. The atom's configuration of whatever here is burning, and I know which one is burning, this is sodium. The electrons in sodium are spinning around and around the atom so fast that as they get hot, they jump out of place. An electron jumping out of place gives off light. We've known about this for a very long time as a human race, but the person who really brought this to our attention was Albert Einstein with his equation of E equals mc squared. Whereas if you get energy going fast enough and you get the mass moving with enough energy, you'll see light. And the speed of that light gives us a color. So I'm going to set away my sparklers for aside for a second, and we're going to go to the real chemistry of it. And we're going to look at individual elements. Again, the four elements are laid out here. I'm going to do one at a time. In order, however, to make them burn, I need a burning medium. And my fuel is methanol, which is a flammable alcohol. The methanol is in my pipette. And what I'm going to do is I'm going to dissolve the metal in the methanol. Now, metal really doesn't dissolve completely, but the compound will break down just enough for us to be able to see a color. So I'm going to set aside my other ones temporarily so we don't have any contamination. The first color you're going to see is going to be the blue methanol flame. But as soon as the blue methanol flame goes away, you'll start to see the color of the metal. And I want to be safe here, and I spoke about contamination. If I drip any of the liquid on my table, other colors will show up that I really don't want to see. I want to see just the color of copper. What's the color of a penny?
Brown.
Brown, and pennies are made of?
Copper.
Copper. So that means this flame is going to burn brown.
Okay. I knew you were lying.
Lying?
Ooh.
Certainly that's not a brown flame. Copper compounds will burn
Greenish bluish.
a greenish blue. My favorite, by the way. This is my favorite color in the spectrum of the metals that we're going to burn today. That is a very pretty blue-green flame. Next time you see a firework goes up, pops blue, it probably had some copper in it. Now that is very hot because it's on fire, so I want to be safe. I just want to remove this, and we're going to take a look at our next one. Up next I had strontium. Now I have given away what color strontium is, but does anybody remember?
Red.
Red. Maybe. Why maybe?
It's red. No, it's red. Ooh.
There's your red. That's strontium. Next time you see red fireworks, you'll know that the metal that's being burned is strontium. Up next, this is an element that we need every day. This is potassium. Most of the food that you eat contains potassium. It's a vital nutrient to the human body. It's all around us, all over the world. But in the natural world, potassium's not just loose potassium. It's combined. It's in a number of salts and organic materials. But if you break those organic materials down, you would get elemental potassium, which is what we're doing right now. And remember, the blue flame is the fuel. But what you're seeing in the tips of the blue flame is the potassium. Do you see what color is there? How would you describe the color of the potassium? It's kind of popping and fizzing. You see it?
The oranges?
It's a very pale pink. It's a pink and orange. You do have to be closer to see it, but don't get your face any closer to the fire.
It is like light pink though.
It's not the most spectacular color.
It's pretty.
But at night, when this pops in the sky, it becomes very illuminated. Last but not least, our friend sodium. Again, ignoring the blue flame, the sodium comes up as a very strong yellowish orange, and there it is there. This is the traditional color of when people say fire. This would be the traditional color of fire, but this is burning sodium. Okay, let's go ahead and set these aside. Okay. Using those four basic colors, we can make any kind of fireworks we want. You see the ones that pop and the ones that go out into the starburst, or the ones that bloom into various colors. To do that, they would layer the colors alongside of each other on a fuse. As the fuse burns, the colors burn, and we would see different colored fireworks. I think we're going to take a commercial break right now, and we're going to come back, and we're going to take a look at some other magic tricks I have in store for us today. But remember, this is chemistry class, so not all magic is what it seems.
The decision is up to you.
Caitlin, speak up.
Hello and welcome back to the BHS Science Lab. We're going to take a look at some more metals.
The metals I have picked out for us today are the Group 1 metals. And the science classes will tell you that these are the earth metals. These are the natural metals that occur in our world. And the three most popular ones, according to the periodic table, if we follow down Group 1, is lithium, sodium, and potassium. And in the family, in Group 2, is magnesium. Now these metals are extremely reactive with the natural world, which is why we don't walk outside and just find some lithium laying around. If it were, it would be combining with things in the air and in the soil and in water to become a lithium compound, commonly known as a salt. But because this is a chemistry lab, I have pure lithium. And pure lithium has to be saved in an oil. It can't react with the air or any water or any moisture. Even if my hands have any sweat on them, it will react with the sweat and it could burn me. Now remember, today's special is about fire and burning metals. So we're going to highlight how these metals react with water. And I'm going to also show you how magnesium reacts with the air around us. Let's start with the lithium. Now I'm going to take the lithium out of its jar and I'm going to place it on this small dish.
Now there's oil in it.
This has an oil in it. And the oil protects the lithium. Now that's a piece of lithium. It's a metal, right?
Okay.
But standing close, you can see that I'm taking this small scoop and I can cut right through the lithium metal. Now, you just can't go out to a car and cut it with a butter knife. But this lithium, the bonds are very weak, so I can cut it. It's like butter. So what I'm going to do is I'm going to drop this piece of lithium in that water. This is a highly reactive situation. You guys can observe what happens. So what's happening in there?
Bubbling.
Bubbles. What else?
Fizzing.
Fizzing, moving. Any fire?
No.
No.
Steam? Smoke?
Well, there's steam. There would appear to be steam and smoke, yeah. But no fire?
No.
Okay. Not very exciting then.
Somewhat.
Somewhat. Lithium is at the top of its family on the periodic table. In order to find something that's more reactive, we have to step down the periodic table. And the next step down the periodic table is sodium. So if I become more reactive as we step down the periodic table, what should you expect from the sodium?
To have more effect?
Let's find out. Is it having more of an effect, like you said?
Yeah.
Yes, it's to us, it's louder. There is visibly more smoke.
More smoke.
Still no fire, though.
Shucks.
So what do you think we have to do?
Go down more.
Go down one more. The next step down is potassium. Sodium is still going. All right, now I got some potassium. I'm going to drop this in the water next. I can't use rubidium because that's a little bit radioactive, and so is cesium, so they're not on our plate today. The farthest deep I can go is potassium. Here we go. What do we expect?
Fire?
Fire. All right, ready? We're going to find out in 3, 2. Why do you expect fire?
Because you're saying that one isn't firing.
But what's happening as we're going?
It's getting more intense.
Okay, well, let's find out. Ready? 3, 2. What do you mean by intense? I'm just kidding.
Whoa. Yep, fire.
Not only fire, but there was some color there.
Yeah.
right? So what color did you see?
Blue, purple, orange.
Okay, so if potassium was a firework, blue, purple, and orange.
Blue, purple, and orange firework.
Very good.
Okay.
Now I have this larger bucket here. Now my question is, I used very small amounts. You saw how much I put in there. What if I put a large piece in here? Would the larger the piece of metal be more effective?
Yes.
Maybe. Let's
Maybe.
find out. Don't second guess yourself. Maybe you're right. What do you want to go with? You want to go with lithium, sodium, or potassium?
Potassium.
Potassium.
I feel like this is going to be dangerous.
Maybe. But like I tell my students, we'll learn together. Ready?
So ready. Woo! It's pink. Ooh! You didn't tell me all that was gonna happen.
So what happened?
That just went wild in there.
Yeah, now the water you said turned
Pink.
pink.
We couldn't see the pink before.
Well, you couldn't see the pink before because what I added to this beforehand was an indicator solution that will turn pink in the presence of a metal burning.
Okay.
So it's a little bit more interesting to watch. But what was the big effect?
At the end,
Yeah, what happened?
popped.
It popped. There was a small explosion. The reason that there was a small explosion is because as the potassium was reacting with the water, it was generating hydrogen gas. Now, for those of you who watched our last special, I created a hydrogen balloon which exploded. This beaker is also now full of hydrogen gas. I used this type of flask because it concentrated the air right about here where the hydrogen started to mix, right in this neck area, and then the flame from the burning metal ignited the hydrogen gas, which gave us a little pop. So I'm going to move this to my fume hood. I'm going to get that gas out of there. But first, since it is flammable hydrogen gas, what do you think would happen if I brought a flame near it?
It would flame. Oh,
But it didn't. Can you explain that?
I cannot.
I can.
Okay.
I should be able to. What happened was in the explosion sucked up all the hydrogen gas and used it all at once. All that's left now is non-combustible, what everyone would call smoke, what we would call air or carbon dioxide. Okay. Can't burn smoke. I'm going to move this to the hood and just get rid of some of the Okay, so we're talking about the reactivity of metals. I still have one more, and it's been hanging up here next to this. Magnesium metal. Now, magnesium metal is not in the same group as lithium, sodium, and potassium, but it's very, very close. It's very similar. Magnesium is a natural oxidizer, which means it will readily combine with the oxygen in the air. It means it's also very hard to put out a flame of magnesium. I'm going to light this magnesium on fire. The cameras that are filming me are going to continue to roll in the magnesium, but I am going to advise my crew to not watch. The people that are watching should look slightly above my head or at the table below me.
I can't look.
No. Now, as you're watching this magnesium ribbon burn, you're going to notice it's a very bright light. As an oxidizer, the magnesium is pulling oxygen in from the air around us, and it's fueling the flame.
It's like tanning bed bright light.
And it was so hot that it actually managed to ignite the wooden holder that I had holding the magnesium. Now what's left?
Some ashes now.
Ashes. Ashes is the common phrase. All that's left really is some magnesium oxide. The magnesium metal, during the burning process, combined with the oxygen in the air to just create magnesium oxide, a powder that is no longer metallic in any property. We're going to take another commercial break. We're going to come back with a magic trick. Maybe. See everybody in a few minutes.
Over 70% of people with learning disabilities are considered social outcasts.
Can you read that next section for us, please?
Like countless others,
Dyslexia is basically a difficulty in learning to read.
Hieronymus and the horrors
Kids with dyslexia have the same feelings as you and I, which means you shouldn't treat them any different.
He witnessed while fighting.
Dyslexia can be overcome, and one day, people with dyslexia might just rule the world.
Welcome back, TV audience, to the Bulldog Shopping Network. Today I have a must-buy product for everyone.
Ladies and gentlemen, have you ever found yourself cold on a wintry night, or alone in the woods, or needing to roast marshmallows in a hurry? If so, this is just right for you. I have new patent pending fire in a bottle. It is the latest craze. Just light it and pour. Fire in a bottle.
Fire in a bottle. That is some fire in a bottle, man. Everybody needs this.
Fire in a bottle.
Fire in a bottle. You should never buy, use, or try to imitate this product. It's fake.
It's fake.
Fake.
Do you know what drugs do to your brain? Do you know what drugs do to your body? There's all types of drugs out there.
Marijuana, cigarettes, pills.
Drugs cause extreme damage to your mind and body. The only way to stay free from the effects is to
Say no
Two.
drugs.
Be drug free.
It doesn't matter. Stop. That water bottle can spend hundreds of years in a landfill. Americans use 2.5 million water bottles every hour, and most are thrown away. If we save just 1 ton of plastic, we can save 1,000 to 2,000 gallons of gas. So just think about it. Reduce, reuse, recycle.
Now welcome back to the BHS Science Lab. So, is Bridgeton water flammable?
Water flammable? I don't think so. But you've all seen the Bridgeton water here at the school, and my students tease us about it all the time. When I turn on my faucets, there's a little bit of rust in it. It's certainly not in the drinking water, that's filtered. But the students always wonder, what's in the water? Well, we're gonna find something out today. Here I have a beaker of Bridgeton water.
Bridgeton water.
Well, it came right out of the faucet. Now wait, hey, you don't believe me, because of course I'm a chemistry teacher. I probably put something else in this water, right?
I believe you.
No, you don't. Take this over to the sink, dump it out, and fill it back up with Bridgeton water, just so we can be sure. Okay.
Okay. Yeah.
So no tricks. You
No
got this
tricks.
right from the faucet.
Yep.
Okay. Just gonna add the water to my bucket. Okay. So here's our dollar.
Okay.
Dollars are made from a cotton fabric,
Yes.
not really paper anymore. So I'm going to put the dollar in the water, and we're going to find out if the water is flammable. Did you see it burn?
Yes.
Okay. So there's the dollar. Did the dollar burn?
No.
No. What burned?
The water?
The water. Is water flammable?
Apparently it is.
Is it? This was a trick, a magic trick. But there's not really anything magic about it. There's a chemical explanation. But I want to leave it off here. Please don't try this at home. Don't burn your parents' money. Don't burn your parents' money. But if you can figure out the trick, write to BHS, and we'll tell you if you're right or not. One more time. You can see the smoke coming off of it. Something burned, but not the dollar. money to burn, or is it? Thank you. Have a good night. The cameras aren't rolling. I'm going to play a little bit with the fire in the laboratory. The teacher's not watching. Yeah. Whoa. Oh!